Gnanam Paramam Dheyam. Knowledge is supreme.
Hello students, this week we will be focusing on stability analysis of feedback systems. Last week we looked at what are the different types of simple feedback controllers like P, PI or PID controllers and how is their performance in terms of disturbance rejection or set point tracking. In each of those cases what we saw was depending on the parameters of the control system like the controller gain, integral time constant or a derivative time constant, the response changes. And we also looked at let us take an example of a proportional controller. We saw that there is always an offset when you use a proportional controller, and that offset keeps on reducing as we increase the controller gain, and in the mathematical limit of that controller gain becoming infinity, that offset goes away. However, in reality it is not always the case. You cannot keep on increasing the controller gain to infinity. So there is always a practical limit in terms of the gain. Other than that, in this week we will see that even though mathematically the maximum controller gain which can be achieved is infinity, many a times that is not possible because of stability criteria. Sometimes the system can become unstable even for finite values of controller gain, and that is why it is very essential to know up to what limit these controller parameters can be varied. So in this week we will use stability analysis to compute these limits, whether they may be the minimum controller gain required or the maximum controller gain which is possible in a feedback control system. So this week we will see what do we mean by stability and what is its relationship, or why do we need to study it in the context of feedback control. And then we will see two different sets of techniques to assess stability of feedback systems. One will be in the Laplace, using Laplace domain analysis, and the other one will be using the frequency domain analysis. So let us get started with what do we mean by stability. So we will take few examples to assess or to get ourselves familiarized with what do we mean by stability, what is instability, and so on. So let us take an example that the first example we are going to consider is of a pendulum. So we had looked at that example right in the first week as well. So let us say this is a pendulum, and in this pendulum it can have two steady states. So by steady state I mean when it is not subjected to any other disturbance, the free position which it can achieve. So this is one of the steady state for a pendulum. And then the other steady state for this pendulum is exactly opposite of that, which is a vertical position for the pendulum. Now let us consider that we are assessing the stability of this particular point, and we give a small disturbance like this. We will notice that eventually the pendulum comes back to the original steady states. By this or this type of behavior we call it as a stable behavior. So this particular steady state we will call as a stable steady state. But same cannot be said about the other steady state of this pendulum. Let us say this is my starting point and I give a small nudge to it, then it will never remain, or it will never go back to the original steady state, but it moves to the other, which is a stable steady state. Because of that we will call this particular steady state as an unstable steady state. Now note that this is still a steady state. If there is no disturbance, the pendulum will remain like this forever, but only when there is a small disturbance it will deviate away from the steady state point. So we have seen that this pendulum has two steady states, one is stable and other is unstable, and all that we characterized based on a disturbance, effect of disturbance, if the system remains close to the steady state it is a stable steady state, if it deviates from that steady state we call that as an unstable steady state. Let us now consider another example of, so we have considered one example of pendulum, and we will consider the second example of exothermic CSTR. Now, you might have discussed this when you have studied any reaction engineering course, because this is a very peculiar system which is typically studied extensively in reaction engineering. So, what we are looking at is a CSTR which is going to convert a raw material A into product B using a reaction of the form A going to B, and this is an exothermic reaction. So, delta H typically negative signifies that it is a exothermic reaction. So, it is going to generate heat, and in order to maintain the temperature, we need to remove this heat by using cooling water. So, that cooling water is circulated in a jacket around the reactor. Now, a CSTR operates at a constant temperature. So, we will see at what are the different permissible values of temperature at which this CSTR can operate, and that can be determined by plotting how the rate of generation of heat changes as a function of temperature, and same way rate of heat removal of heat, how does that change as a function of temperature. Generation or removal. So, rate of heat generation will be given by rate of reaction, which will be K0 exponential minus E by RT, that is the Arrhenius form, times Ca. So, it is rate of reaction multiplied by delta H. So, that is the rate of heat generation, and you can see that the effect of temperature is reciprocal of inverse exponential, and as it turns out, if I plot this rate of heat generation as a function of temperature, the curve which we typically get is of this form. Now, let us look at rate of heat removal. It can be given by UA T minus Tc, where T is the temperature of reactor and Tc is the temperature of the coolant. So, you can see that it is very much linear in terms of the reactor temperature. So, that will be like this. So, now in order for the CSTR to operate at a constant temperature, rate of removal of heat should be equal to rate of generation of heat. So, there are 3 points at which this CSTR can operate. So, let us say at this point these two rates are equal, at this point these two rates are equal, and this is the third. So, there are 3 steady state temperatures at which this CSTR can operate, and we will look at now whether these are stable or unstable. So, let us start with steady state 1. So, we are looking at this steady state, and let us consider that there is some disturbance in this system because of which the reactor temperature increases. So, let me just show these temperatures as well. Now, let us consider that because of the disturbance, this temperature increases some new value, let us say this is T1 dash. So, now when the temperature increases, what can we see? We can see that the rate of removal of heat is now more than rate of generation of heat. So, there is net deficit of energy or net deficit of heat in this reactor, which will cause the reactor temperature to decrease. So, eventually that temperature will again come back to T1. Same logic we can apply if the temperature of if the disturbance had caused the temperature to reduce, then the rate of heat removal is less than rate of heat generation. So, there is surplus of heat in the system, and again it will move the temperature towards T1. So, any disturbance, whether a positive temperature disturbance or a negative temperature disturbance, both these disturbances eventually gets automatically countered and the steady state temperature remains same as T1, or the system returns to the steady state temperature T1. Same thing can be analyzed for T3 as steady state 3 as well. So, we can say that steady state 1 is stable. Let us look at steady state 3 and say that if there was if the disturbance cause the temperature to increase to T3 dash. So, at that point the rate of removal of heat is greater than the rate of heat generation. So, again there is a net deficit of heat into the system, the temperature will drop to T3, and same thing is true if the disturbance had caused the temperature to go down, which case again it will increase the temperature. So, both these steady states are stable because the disturbance is not able to move the system away from the steady state. Now, let us try to analyze whether steady state 2 is also stable or not, because that is the steady state which is typically of interest. So, let us say at T2 the disturbance causes the temperature to go to T2 dash. So, when we move to T2 dash, we notice that the rate of heat generation is more than rate of heat removal. So, there is a surplus of energy or heat into the system, so that it will cause the temperature to increase. So, you will see that this increase in the temperature caused by the disturbance results in further increase into the temperature, and eventually that temperature will stabilize at T3. If we had given, if the disturbance had reduced the temperature of the system, what you can again find out that the rate of removal of heat is more than rate of heat generation. So, there is net deficit of heat and the temperature will keep on further falling down and eventually it will go back to T1. So, the steady state 2 is unstable because a disturbance when the disturbance affects the system can no longer remain at the steady state and it moves to some different steady state. Now, let us close this discussion with two familiar examples of liquid surge tank. So, in liquid surge tank, let us consider a case. So, this is input and F out. Let us consider a case when the outlet flow rate can be independently manipulated or it is independent of the height inside the tank, and which is pretty much possible if there is some kind of a pump which is taking out this much flow. So, that flow will not depend on the height inside the tank. Now, in this case, let us consider a disturbance that F in increases. Now, as F out is independent of height, F out will remain the same as the earlier value. So, there is net accumulation of material inside this tank. So, height will keep on increasing indefinitely till the tank overflows. So, this particular disturbance, because of this disturbance, the system no longer remains at its original steady state, which was, let us say, height Hs, and it continuously, the height keeps on increasing and eventually the system leads to instability. In some sense it goes to overflow. So, this is an unstable system. Same thing can be proved if the Fin was low. If Fin had decreased, and then in that case the height will continuously decrease, resulting into the dry out of the tank. Now, let us consider a variant of this process, same liquid surge tank. but now this F out depends on H. It may be a linear dependence if the flow is laminar, it may be square root dependence if the flow is turbulent. So, let us say F out depends on H, and we look at the same disturbance scenario here. That F in increases. Now, as F in increases, initially F out is same as the steady state value, the height will increase or height will tend to increase. As height increases and F out is proportional to the height, the F out will also start increasing, and eventually there will come a time when the height inside the tank is sufficient enough that the new F out, which is proportional to this that new height, will be equal to F in. So, the increase in the height, so there will be increase in height, but not indefinitely. And ultimately height settles to a new value close to Hs. So, what we have seen that when the disturbance is affecting this particular system, the system is not really unstable, that it is indefinitely moving to the boundary of the system. The height does indeed move from the original steady state, but it still remains close enough to the original steady state. So, this kind of system will still be stable, and we will see why this kind of stability is different from the stability which we saw for the pendulum example or a CSTR example, where the system had returned to the steady state. So, in order to do that, let us now look at the formal definitions of stabilities. So, the stability is defined in two broad terms. One is a weaker definition of stability and other is a stronger definition of stability. So, let us start with a weaker definition of stability, which is also known as marginal stability. So, now marginal stability, what do I mean by this is, if the system is disturbed by a bounded input like for example a step input, that we have made a finite change into the input and the response of the system is also bounded, then the system is said to be marginally stable. So, what this means is, the key points here in this definition are that you are giving a bounded input, and if the output of the system or the response or output of the system is also bounded, then the system is called to be a marginally stable system. It is also known as bounded input, bounded output stable. So, all it says that if I give any bounded input and the system remains close to the steady state, then that type of system is known as a marginally stable system. So, our liquid surge tank which had the outlet flow proportional depending on the height of the tank, that is a marginally stable system. If you look at the steady state of the pendulum, which was like this, as well as the CSTR steady state 1 and 3, in all these three cases the output remained or came back to the original steady state. That means it was still bounded or it was close to the original steady state where the closeness being equal to 0. Those are also, so marginal stability is also present in those type of systems. Now, this particular definition of stability was given by a scientist known as Lyapunov back in 1890s when he was studying the stability of planetary orbit. So, you can see that the connection between the theory which was developed to study the orbits of different celestial bodies, we will be using this theory to assess the stability of our chemi systems. So, he was the guy who is responsible for defining this type of stability notion. So, this is also known as Lyapunov stability. And there is a stronger, this is a weaker definition of stability. There is also a stronger definition of stability known as asymptotic stability. So, what do we mean by asymptotic stability is? So, this is a stronger definition of stability. So, it says the system is marginally stable So, it says that if the input is bounded, the response is also bounded, and in addition to that the system returns to the original steady state. So, this is a stronger definition of stability because of the second criteria. It says that not only the output remains bounded, but it goes back to the original steady state. That means the system automatically rejects the effect of disturbance and goes back to the original steady state. So, the pendulum, this position, the downward position, as well as CSTR steady state 1 and 3, all these three are asymptotically stable steady states. So, when you have asymptotic stability, indirectly it automatically means the system is marginally stable. So, if we look at all the examples which we have seen, so pendulum downward position steady state is asymptotically stable. Upward position is unstable. Then we look at CSTR, steady state 1 is asymptotically stable. SS2 was unstable, SS3 was again asymptotically stable. And then we looked at the search tank, where F out independent of height, it was unstable, and when F out is dependent on height, it is marginally stable. We will now be using these definitions whenever we were trying to assess the stability, and what you can also realize that okay. So, let us now see why do we need to care about stability analysis and what is its relationship with the feedback control. So, right in the first week when we were looking at what are the functions of a feedback system, one of the important function of a feedback system was to stabilize an unstable process. So, feedback control is able to stabilize any unstable process, like the unstable process which we have studied. So, we had seen that this particular liquid surge tank system is unstable, and if we simply have a feedback control where we are controlling this outlet flow by using, let us say, P control, PI or PID control, then any disturbance in Fin can be regulated and the system can be made stable. If we use a simple P controller, then the system will become marginally stable. If we use a PI type of control or PID control where the offset can become 0, we can stabilize it at the original steady state, so the system can be made asymptotically stable. So, one of the important characteristic to study stability is if we want to stabilize any unstable process like an integrator, then stability analysis will tell us what is the minimum amount of feedback which is required. So, it will tell us the minimum value of controller parameters which are essential in order to stabilize that process. Then stability, the feedback system can also convert a marginally stable system into a asymptotically stable system. Again, as we look at the surge tank example, this particular system is marginally stable because we do not have any control on that. But let us say if I change this valve opening using a PI controller where it opens or closes the valve depending on deviation of this height from the steady state. By using a PI control or a PID control, I can maintain this height irrespective of the disturbance. So, I can convert this marginally stable process into an asymptotically stable process. And lastly, one of the most important area why we should be studying stability is that other than these advantages of converting an unstable process into stable one or a marginally stable into asymptotically stable, feedback control can actually destabilize a system. So, here I have shown a simple plot of 3 CSTRs in series, and so let us consider that a system is we have 3 CSTRs in series. Where this is the input and this is output, and in order to control this outlet concentration, we have a feedback system. So, we will measure this concentration. Then there is some set point value. We have a controller and it is going to change this composition, and let us say we are using a P control which has a controller gain as the input. Now, this without any controller, this is a stable process, because if I have a finite change in the inlet concentration, the outlet concentration will also change by a finite amount, and the corresponding transfer function, let us say if I take V equal to 2 units, F equal to 1 unit and the rate constant as 0.5 unit in corresponding units, then the transfer function Ca3s over Ca0s comes out to be 1 over 8 s plus 1 cube. So, it is a stable process, all the poles are at -1. So, we know that this open loop system is stable. Now, let us say I introduced a P control, so that I want to be able to control this outlet concentration in the presence of any disturbance. Here I will show you the plots when we want to change this Ca3 to a new value, and let us see how the controller performs. So, when I use a small value of controller gain, let us say like Kc equal to 10, you can see that the system moves towards the new steady state without much of an oscillation, and this response is stable. If I increase this controller gain to, let us say 25, the oscillations increase, again the offset also decreases. If we increase it to 50, you can see that the oscillations have increased tremendously, and all we are doing increasing controller gain because we want to reduce the offset. And lastly, let us say if I use a controller gain of 70, an interesting thing happens. You can see that the system no longer remains stable. So, all these oscillations, rather than being decaying, they are actually increasing the oscillation, and the system is going to move towards instability. So, here what I want to convey to you is that there is always some limit in terms of the controller parameters which you can use, which is clearly highlighted from this example, that if I keep on increasing the gain, after some point the system just becomes unstable. So, this is a very worse situation which as a process engineer you can land yourself in, that the original process was stable, and because you added a controller on that, you have made it unstable. So, the system would have performed better in the absence of a controller. So, in summary, what it tells me that stability limit is very important, because it will kind of put a limit on how much is the rangeability of the controller parameters. So, we will take a short break here, and after we come back we will see how is this relationship between the stability and feedback control parameters, and we will see how this can be assessed and how can we compute these bounds on the controller parameters. Thank you.